Okay, so number 2. Now, the steps, if you have them where you can see them and do this at the same time, that's good. First of all, step 1, I'm going to draw a picture. So, what shape am I going to draw? A circle. And we just want our pictures to be as simple as possible. It's a circle on the ground. And what's happening to this circle?
It's leaking.
But the circle's not leaking.
Oh. The radius is increasing.
The whole thing, it's getting bigger, right? The circle of water is getting bigger because something's leaking on it, okay? So it's dripping on there, and this circle has, now, once you know what shape, you know, it's kind of easy to reverse steps 1 and 2, because if you're dealing with a circle, you're either going to be finding circumference or area of a circle. So what in the problem do they talk about? Do they talk about area or circumference? They talk about area. So basically, step 2, I can pretty much write my equation, area of a circle is pi r squared. Don't worry, I mean, I wish you knew all the formulas, but I'm pretty sure you don't. So the day of the test, I'll just put a bunch of formulas up so you don't have to memorize them. I mean, the formulas you need will be on the board for the test. So, all right, so the area, this was our formula. So now that means that I have to put, basically here's what I have to do, and here's the different part for step 1. I am not just figuring out what A is and what R is, okay? Because the key is I've got rates of change in my problem here. So I'm also, every variable that I have in my equation, not right now,
Okay.
So every variable in my equation, at least most of the time, should have its own rate of change. So for every variable that's here, I should have an A, and then I should have its rate of change. What's the rate of change or the derivative of A? We just talked about how to get those on the last page, like right down here. That's what we just talked about. So what would be the derivative of A? dA over dt. All we're getting is names of variables. You have to put all the numbers in the problem with a variable. dA over dt is a variable. It's the rate of change of area. So this is the rate of change of area right there. So what is dr over dt? What is that? What words is that? dr over dt. Rate of change of the radius. R is the radius, A is the area. dA over dt is how fast the area is changing. dr over dt is how fast the radius is changing. So now I go look at the numbers in my problem and say, okay, the number that stands out, it says radius is 12 centimeters. So that means R is 12 centimeters. Okay, well, why isn't it 9? Why isn't it 9 centimeters? That's the rate, because it says the radius of the pool increases at a rate of 9 centimeters per minute. Please listen. You can use the units on the numbers to tell you whether it's a rate of change or not. A rate of change is always with respect to what? Time. So any variable that is a rate of change will have a per minute, per second, per hour. So I know that 9 centimeters per minute is a rate of change. It is one of these two. Is it the rate of change of area or radius? Radius, because it says the radius of the pool increases. So this is 9 centimeters per minute. Okay. Now, I don't know the area. I don't need to know the area, actually. That's okay. Do they ask me to find the area, or do they ask me to find the rate of change of area? They asked me to find the rate of change of area. That's my question mark. That one, I don't really need. I don't need it. Okay, so step 1, I'm done with it. Step 2, I have my equation. Now step 3, taking the derivative of both sides implicitly and using the chain rule. Okay, this is really easy. Just watch. I start with A and say, what's the derivative of A? No, the derivative of A. Just A, dA over dt. I take the derivative of both sides. Basically, every variable is like a y in implicit differentiation now. In implicit differentiation, every time you had a y, you took its derivative times y prime or dy over dt. Now we take the derivative of A, which is 1 times dA over dt. Equals, what's the derivative of pi r squared? Power rule. 2 pi r. But I took the derivative of r, so times dr over dt. That's the chain rule and implicitly. I took the derivative of the variable r, so then I multiply by dr over dt. Thank you. Zach? Zach and Chloe, you have notes to leave at 2:45. So, all right, so I'm done with step 3. Now step 4, I plug in everything that I know and I find the unknown. So I'm looking for dA over dt, and I know r is what? R is 12, and dr over dt is 9 centimeters per minute. And I mean, the labels can help you. How many of you have had dimensional analysis? Okay, dimensional analysis, I mean, using dimensions, that can tell you where things go, where they plug into. It can tell you, if you use dimensional analysis, it can tell you what label you should have on your answer, because incorrect labels on these, they're not correct. If you have an incorrect label, you're not right. Okay, so, did you see what I did from here to here? I took my derivative equation and I plugged all the things into it that I knew. So now, you can leave your answers in terms of pi, which means don't multiply by pi. Leave the pi and take 2 times 9 times 12. 2 times 9 times 12. 216 pi. Now the label, centimeters times centimeters. Centimeters squared per minute. The one, well, yeah, the one above it says seconds. Okay, we're just going to move on. We're going to take a look at number 3 now, and then we'll go back up to number, we might not go back to 1. We might go to the back. Okay. So, number 3. A hypothetical cube grows at a rate of 8 meters cubed per minute. How fast are the sides of the cube increasing when the sides are 2 meters each? Okay, so what shape do we have? Cube. So step 1, I've got a cube. The cube is a box and all the sides are the same. So, and we're talking about, well, I don't know if we're talking about the volume or the surface area. Yep, S for sides, so S would be the side. So if we know that aren't all the sides the same? Now, am I dealing with volume or surface area here? Okay, look at this value right here. The cube grows at a rate of 8 meters cubed per minute. Is that a change in volume or surface area? That's a change in volume. How do you know it's volume? It's cubed. Very good. Volume is cubed. Surface area and area are squared. So this is dV over dt is 8 meters cubed per minute. So I'm dealing with the volume of this cube. So what's the formula for the volume of a cube? It's S cubed. So there's step 2 already. So S, what is the S in my problem? 2 meters. And so I should have a ds over dt. Do I know a ds over dt? Isn't that what it asks for? How fast are the sides of the cube increasing? That's what I'm asked to find. That's ds over dt. How fast is something increasing, decreasing? That is a rate of change. That's a derivative. Okay, so now I just need to take the derivative of the volume equation. So what is the derivative of V? dV over dt. 1 times dV over dt. The derivative of S cubed. 3S squared times ds over dt. So now I plug in. The dV over dt is 8 meters cubed per minute. The S is what? 2 meters. And I'm going to square it times ds over dt. So let's see, I've got 8 meters cubed per minute, and 2 squared is 4 times 3 is 12 meters what? Squared. times ds over dt. Now you don't have to write the labels as you're working. You don't have to write the labels in like I'm doing right now. In fact, the next problem I won't do it. But I want you to realize that you can figure out the label in the final answer by using the dimensional analysis. So now, how am I going to get ds over dt by itself? Divide both sides by 12 meters squared. So ds over dt is equal to, can I say, what?
Meters per minute.
8 over 12. What goes into both of those? 4, 2/3, and then the meter squared cancels with 2 of the meters on top, and it's meters per minute. So 2/3 of a meter per minute is how fast the sides will increase when the volume